when I go about calculating expected value, I always find it really helpful to set up a table with the X values and the probabilistic values underneath. So in our case, we have a person who has $20,000 and a 50-50 chance of losing it and dropping down to a wealth of $10,000. So we'll put a 0.5 down here and a 0.5 down here. At this point, let's go ahead and calculate the expected value. I'll use, this is my notation for expected value, but I think your professor's is just EX without the parentheses. So just bear that in mind. Expected value of X equals, we take each of our X values and multiply them by their corresponding probabilities and then add them together. We learned this back in Eco 329. I sure hope you didn't forget. Multiply this out. And this comes out to be $15,000. That's the expected value of this gamble. Now, when you're being asked what actuarially fair insurance costs, it's the difference in the wealth you have and the expected value that you'd end up with if you took the gamble. So actuarially fair insurance, actuarially fair insurance is your wealth, or I should say the cost of actuarially fair insurance is your wealth, is initial wealth minus expected value of gamble. So in our case, that comes out to be initial wealth was $20,000. Expected value of the gamble was $15,000. So actuarially fair insurance cost $5,000. Now, I think the next part of this question tells us we must show that we would choose the insurance over the gamble. We can do this graphically. One of my favorite ways to do this is graphically. So what we're told initially is that this person is risk averse. Let's actually pause for a second and talk about risk aversion real quick. So, ooh, that's an ugly looking graph. We've got three possible graphs, and on each of the x-axes we've got wealth. So wealth, wealth, and wealth. But on the y-axis we have utility, 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 utility. And this person is risk averse. This person is risk neutral. And this person over here is risk seeking or risk loving. Okay. Here's how their not indifference curve, but their utility curves look based on wealth. So here's risk averse utility curve. Here's a risk neutral utility curve. And here's a risk seeking, risk loving utility curve. Most people, probably you included, are like this, although I've seen some of you guys gamble and maybe I think you're risk seeking, you're risk loving, but most people are risk averse. They would rather have, are they much, I don't want to, obviously, we'd obviously rather have more. Obviously, all of these graphs are increasing. So obviously, U prime of W is positive. That means if you have more money, you will be happier. Duh, that's obvious. But for the risk averse category, U double prime of W is negative. This says that we get less utility, we get less of a utility bump for higher levels of wealth. Yeah, period. I think that's all I can say. We get less of a utility bump for higher levels of wealth than we do for lower, I'll say, than we do for lower levels of wealth. And this kind of makes sense. I want you to pause for a second and think of a game where, and I give you two scenarios, okay? I'm going to give you two possibilities, all right? Choice A. I give you $500,000 straight up. Choice B. We will flip a coin. If it's heads, you get $1 million. And if it's tails, you get $0. So who in the audience would choose choice A, and how many of you would choose choice B? I can guarantee you many of you would choose A, even though A and B have the same expected value, right? There's a guarantee of $500,000, or there's a 50-50 shot at $1 million, which again, if you do the expected value calculation, has the same $500,000 value as choice A. Many, if not all of you, would prefer choice A. I would prefer the sure thing of $500,000 than just the million. So the kind of rationale behind that is, what can I do with $1 million that I couldn't do already with 500,000? Okay, 2 vacations, or I don't know, 2 Coke fueled benders. I mean, okay, yeah, sure, but obviously you can get more for $1 million than you can get for $500,000. But when you're talking about where $500,000 is on your utility curve, so there's five, let's just say it's 500,000. This is 100,000, a million. Where this comes up on our utility curve here versus a million isn't that much higher. We can see that we're gaining quite a bit of a bump here as a result of having $500,000 than we do from an additional $500,000. So most people are risk averse. And we'll talk about, we're going to be using this graph on the left to show why the person will prefer insurance over taking the gamble. So we'll do that over here. We were told, like I said initially, that the person who's making this decision is risk averse. So we're going to draw some sort of concave down. I get OCD about this. There we go. Concave down utility curve. So here's wealth. Here's utility. And the gamble represents the straight line connecting the two. So let's say graphically, the gamble represents the straight line drawn between the two outcomes. So let's find those two outcomes. One of those outcomes was 100,000. Let's put 100,000 here. No, sorry, not 100,000, 10,000. So 10,000 here, and then we'll put 20,000 here. And then we'll go mark these dots. Let's mark this in purple. Okay. The gamble represents the straight line connection between these dots. So it represents this guy. Now notice, and then the expected value will fall on the straight line drawn. And in fact, we know what that expected value is. It corresponds to a wealth of 15,000, which is here. However, check it out. Look at their utility. This dot is below the curve. It's below the utility curve. So they're actually, the utility from this is not as high, despite the fact that the expected value corresponds to 15,000, not as high as this dot here. So this dot is with insurance. And why is that dot with insurance? Because remember, with full insurance, they were going to be paying. So here's what ends up happening. We can copy this table and say, well, what happens in this situation? Well, now the person says, you know what I'm willing to do? I'm willing to give up $5,000. But if I get sick or I have that disease or whatever happens, I get $5,000 back. So here's what happens though. This number now becomes 15,000. And this number now becomes 15,000. And basically, no matter what, they are left with 15,000. This has the same expected value. This expected value of 15,000 has the same result as what we had before when it was this table back up here. And yet, this point is a little bit higher graphically on the utility curve than this point. This is with the gamble. This point here with insurance is higher than this point down here that's with the gamble. So the insurance is the higher utility value. Another way we can do it is, well, actually, yeah, sure. Another way we could do it is we could ascribe a utility function. So let's say the utility function, a common utility function is the square root function. So this is commonly used as your utility of wealth function. Not always. The reason it works so well is because the square root graph looks like what we know or what we come to expect a risk averse profile to look like. Okay, so that's what the square root graph looks like. It's standard for what we expect to see for a risk averse person. If you recall, a table that we made earlier was one that had the wealth values on it. And I probably shouldn't use X, I should use W to indicate these are wealth values, where we had 20,000 and 10,000, 0.5 and 0.5, and we'll put probability of W here. But again, people don't operate on the amount of money they'll have, they'll operate on the utility they'll get from that money. So what we're gonna do is we'll say U instead, and P of U. How do I find the corresponding utilities of $20,000 and $10,000? Well, all I do is take them and plug them into my utility function. That's all I need to do. So I'm going to take 20,000 and 10,000 and plug them into square root of W. If I do that, I get 141.4. And if I plug in 10,000, I get 100. So I get 140, or not, sorry, not 140. This is still 0.5 and 0.5. These don't change. The probability values don't change. And now let's find the expected utility. So we'll do half of 141.4 and half of 100. I'm going to try and do this in my head here, but I think it's going to come out to be 120.7. So that's our expected value if we take the gamble. So this is expected utility, I should say, expected utility or happiness of taking the gamble. What's the expected utility of not taking the gamble? That is to say, or paying for insurance. Well, in that situation, recall that the table looked a little bit different. In that situation, both outcomes for wealth were 15,000. And so when I go to construct my utility, actually, there's no point in even saying 15,000 times 0.5, 15,000. This is just now, there's a 100% chance of you getting, there's a 100% chance of you getting $15,000. It makes no sense in having two of the same value in the same probability table because they could just combine. So 15,000, a guaranteed $15,000. What is our utility here? Well, it's we need to convert this to a utility table. The square root of 15,000, and you grab a calculator real quick. 122.47. And then of course the probability of that is 1.0. So when I go to find the expected utility here, I get 1 times 122.47, which is 122.47. What's better? In what situation are we happier? 120.7 or 122.47? Seems as though we are happier with the insurance than we are with the gamble. Now, the only thing that I would caution you against doing for this problem is using the utility function of square root of w. I don't believe that the utility function of square root of w was ascribed here in 7.4. It was just said that all you knew about this person was that you had a risk-averse individual. That's all you were told. That could mean their utility function looks something like square root of w, but that doesn't mean that it is. It could be something different like ln of w or negative e to the negative w. Something like that I think is also concave down. But my point being is that you could, if you want to, throw in and say, like, let's pretend that the utility function for this person is square root of w to give some sort of risk-averse behavior, but they didn't tell you that that was their utility function. So we did it algebraically, and we also did it, if I undo quite a bit here, we also did it graphically. I like the graphical version because the graphical version doesn't rely on you stating what the utility function is, only that the person is risk-averse, which has this shape. Do I know that it's square root of w? No. Do I know it's ln? No. Do I know it's some other wacky function? No. But I know it's going to be concave down, and so I can see where these points are. The point down here with the gamble provides a lower utility than with insurance. Okay, I've said enough about 7.4. Let's look at the next question. We've got, it's funny because this person does have a utility function of square root of w. I'm going to change it to w as opposed to x. I think you'll live with it. Starting wealth of 30,000, offered an opportunity to invest all of it in a new company. Okay. Oh, you know what? I think I forgot part B. Part B from 7.4. Let me not skip ahead just yet. There's a fair policy covering the complete loss. So we talked about the fair policy. The fair policy covering complete loss costs 5,000 and provides a utility of, I forgot the number already, 122.47. Okay. And again, that was if we assume u equals square root of w. So that was an assumption we might not have made, maybe shouldn't have made, but we'll continue assuming that for the purposes of doing this algebraically, and then I'll show you graphically what that would look like. Actually, graphically, well, I'll just draw it again graphically. All right, let's do a fair policy covering half the loss. Okay, so a fair policy covering half the loss. Remember, there were $20,000 and $10,000, and then 0.5 and 0.5. and then wealth, and then probability of wealth. Well, remember that a moment ago we said $5,000 covers the whole loss, right? So covering half the loss would cost $2,500. So if to cover a policy covering half the loss would cost $2,500. Go figure. It's half of what it costs to cover the complete loss. So this is going to be minus $2,500, but this is going to be plus $2,500. So we get a new number of 17,500 and 12,500. Let's go ahead and convert this to a utility table. So this is square root of 1750, 132.29. And then we'll do square root of 125, 111.8. Okay, we still have a 0.5 here, still have a 0.5 here. Let's go ahead and do half of each of those numbers. 0.5 times 132.29 plus 0.5 times 111.8 gives me 122.045. 045. And once again, let's compare these two utility values. This situation makes us happier. Let's see it graphically. I'm going to draw this bend quite a bit. Okay. So we've got 100 and 200, and we'll put this dot. I really don't like this curve. I'm trying to really make this curve pretty pronounced. Yeah, that's much better. So this dot and this dot represent the full gamble. Let's do this in purple. This line represents the gamble. Complete no insurance whatsoever. So that is 0% coverage. We talked about this scenario where we'll do this in green. This was this dot, and we'll say this dot represents 100% coverage. And now we're going to do a blue situation. Well, blue situation is, like I said, where half the loss, where we end up at 175. I don't want this in green, I want this in blue. 175 or at 125. And so here are the dots we get with that. Once again, I'm going to draw the line connecting these two. And we'll say this line represents 50% coverage. Okay. What would we prefer? Again, we see that the green dot is just a bit higher than the blue line, and obviously we knew it was higher than the purple line. I do want to point out though that how much happier the person's becoming by having some insurance, right? We were worst off here. This was the worst case scenario of happiness. This was the best case scenario of happiness. And this guy was not, it's at least better than no insurance. Cool. Okay, and I think that's all you have to do graphically to show your answer to part B. Okay, now I've said what I need to say about that, and I can move on into the next question. Next question says, we've got, U of W equals square root of W. And we have an investment that we can make where we put in $30,000, where we can wind up with 11,000 more. So that is to say, we get our investment of 30,000 back plus 11,000 on top of that, or we lose half of our investment. We are told there is a 40% chance we'll lose that money, and therefore a 60% chance we'll gain that money. And the question is, first question is, give the expected value and standard deviation of the wealth if they choose to invest. Expected value is pretty easy to do. 0.6 times 41,000 plus 0.4 times 15,000 gives me expected value of, let me get a calculator real quick. 30600. Now notice this is more than 30,000 of the, this is more, this expected value is more than our starting wealth. But that doesn't necessarily mean we would prefer to invest. Okay, so that's something we'll cross a bit later, I think maybe in part B. But let's move on to calculating a standard deviation. To calculate a standard deviation, you're going to subtract the mean from each of those. That's, again, this is the mean or expected value from each of those X values and then square it. So watch carefully as I do this. I'm going to take the 4,100, subtract the 3,600, or it's not 30,600, and then square this number. We'll do the same thing for the 15,000. Take the 15,000, subtract the 30,600, square it, and the probabilities do not change. These will stay as 0.6 and 0.4. When I calculate the expected value of this, or at least when I go to do the take each X value and multiply it by its corresponding probability and add them together, this will give me the variance. So let me go ahead and calculate this. 41,000 minus 30600 gives me 10,000. Oh, sorry, square this. I get 10810 is 108160000 times 0.6 plus. Then we have 15,000 minus 30,600. We'll square that to get 24336 with 4 zeros. And this is being multiplied by 0.4. Adding this all together, 0.6 times sec 24336 000 16224 000. Now be careful. This is the variance. I yet to find the standard deviation, but the standard deviation is pretty easy to do. The square root of variance equals standard deviation. So let's go ahead and calculate that by doing the square root 16224 to get an answer of 127.37.3. So standard deviation equals this guy. And this guy over here was our expected value. So that's our mean mu, and this is our value of sigma. Okay, that's part A now done. Part B asks, showed that she would prefer not to invest. Okay. As is standard, we need to not calculate an expected utility. Sorry, not an expected wealth, but an expected utility. So let's convert these wealth values. I'd rather not say X here, but rather say W. Let's convert these wealth values into utility values by using the function provided. So now we're going to say utility and the probability of this utility. Remember, how do I get the corresponding utility values for each of these levels of income? I just take them and plug them into my utility function. So if I do square root of 4,100, I get 202.48. And if I take the square root of 1,500, I get 122.47. Let's put the utility or the probabilities here and go ahead and calculate the expected utility. It would be 202.48 times 0.6 plus 122.47 times 0.4. This gives me a lot of calculations going on here. Give me a sec. 170.476. So this is the level of happiness. This is the level of happiness or utility when investing. If we don't invest, then we just simply keep our original wealth of $30,000. This needs a corresponding utility. By the way, you don't really need to set up a table for this. You could say, okay, my wealth is in $30,000. and there's no alternative outcome. So this is a probability of 1. So this seems a little silly because I don't need to make a table. The reason the table is helpful is when there's more than one scenario, but I don't need to make a table when there's only one outcome. I do need to convert it to a utility though. So I need to take the square root of $30,000, and that should give me something like 173.2 square root of 30,000. 173.2, yeah, 21. This is the level of happiness when we do not invest. Where are we happier? We are much happier here. So do not invest. Okay, that's your answer to part B. Let's clear the board here and go on to part C. Suppose now that they are offered a share of an opportunity to take a alpha % share in the venture. So here's what this looks like. What the table says makes it sound as though her payoff is 41,000 alpha if the investment is a success, or 15,000 alpha if the payoff is not a success. But there's one critical thing you have to remember is that let's say this. Let's say I have, again, you have to not forget that she has $30,000. So if she says, you know what I want to do is I want to take a third of my money and invest this, then I want to keep the remaining 20,000. So this is saved or kept. Okay, so I'm going to keep that. So this value here it shows what's invested, but it doesn't show what is kept. Now, how do we figure out what is kept? Well, you got to remember that alpha is the fraction invested. So for instance, alpha equals 0 means don't invest or no investment. And alpha equals 1 is invest everything. Invest all $30,000. And we just talked about these two cases specifically. We said that not investing gave a utility of 173.2, and I forgot what this guy was, 170 something, 170, I forget. But we knew that not investing gave us the highest utility. So the question is, what was something like alpha equals 0.5 represent? Well, half of your money, so this would be $100 or $15,000 would be invested, but I would still keep $15,000 over here, and that needs to be reflected in this table. So what I'm going to say is I'm going to say plus 30,000 times 1 minus alpha, and that's going to be the same thing over here, 30,000 times 1 minus alpha. So first off, you might be wondering, why 30,000? Well, this is the money that we would otherwise have had we not invested. And why 1 minus alpha? Well, remember, if alpha is the fraction that's invested, then 1 minus alpha is the fraction that is saved, right? If 30% of our money is invested, then 100% minus 30% or 70% is kept, okay? So these are our wealth values. And we have a 0.6 here, and we have a 0.4 here. But of course, I don't really care about maximizing my wealth. I care about maximizing my utility. So let's delete this stuff over here. I don't care about wealth. I care about utility. So let's put utility and probability of this utility on over here. How do I get utility from these wealth values? Remember, you have to remember that the utility function in this case is to take the wealth value and square root it. So we have these wealth values here. We square root them so as to get the corresponding utility values. Okay. At this point, I'll do a little bit of the math, and you probably should do a little bit of math yourself. If I want to go find the expected value of my utility here, I just take the 0.6 and multiply it by this. And then I say plus 0.4 times this guy. So this is what my expected utility would be for any given level of alpha. You can try this yourself. If alpha equals 0, we should get 173.2 from this, because it means that we didn't invest, right? If alpha equals 1, we should get, I forgot the number, 0.6 times square root of 41,000 rather, plus 0.4 times square root of 15,000. 170.48 for this. and try it yourself. Pause the video. See for yourself that if you take alpha equals 0 and plug it into this monstrosity of an equation, use a calculator or use Wolfram Alpha. Notice that if you plug in 0, this pink term and this pink term go away. Whereas when you plug in 1, this purple term and this purple term go away. So it makes your life a little bit easier. Another question is, what value of alpha maximizes this expression? Now, I hope we've made it far enough in this class and to know that anytime we're being asked to maximize a function, we need to, didn't mean to switch to green, but whatever. To maximize an expression, take the derivative and set it equal to 0. Then we solve. Now at this point, I'm gonna say, you know what, you should know how to take a derivative. We could first off, before taking a derivative, simplify the insides of this, insides of these square roots, but I'm not gonna have you do that. I'm just gonna say, you know what, let's just use an online calculator. Okay, so I'm going to toggle on over to Wolfram Alpha and say, I'm going to snag my whiteboard. Oh, I don't have it. Maximize 0.6 times the square root of 41,000 times x plus 30,000 times 1 minus x plus 0.4 times the square root of 15,000 plus 30,000 times 1 minus x. Cool, let's see what this gives us. This tells us that I screwed up. Oh, this needs an x. 126 over 583, or approximately 21.6% of our money goes to the investment. So there's x equals 0.2162. Alpha equals 0.216. So that says we will invest approximately 22% of our $30,000. We will keep the remaining 78%. This will make us the happiest. Okay. There's one last part, I believe, part D. Oh, no, we did. That was it. Oh, sorry, I skipped part C. It just says show that its derivative is positive at alpha equals 0. Okay, well, I do have to do some derivative stuff then. Crap, I didn't think we have to do any derivatives, but okay. Let me show you how to do calculus, because I know some of you out there are like, I don't know how to do calculus. Please hold my hand. Sure, you got it. So let's simplify this a little bit. 0.6 times the square root of what ends up being 11,000 alpha plus 30,000 plus 0.4 times the square root of 30,000 minus 15,000 alpha. Okay, we are going to take the derivative of this expression and evaluate it at alpha equals 0. Now, what I'm going to do first before I take this derivative is remind you that some of the best ways to take the derivatives from square roots is to write those in parentheses and put it to the power of 1/2. So the square roots are gone and now erase the power of 1/2. When I go to take this derivative with respect to alpha, it's not a partial derivative, of expected value of utility, I get 0.6 times the 1/2 comes down in front times 11,000 alpha plus 30,000 to the power of negative 1/2 times the derivative of my inside function, which is 11,000. That's chain rule coming into effect there. Chain rule, don't forget it, you need it. Plus 0.4 times 1/2 times 30,000 minus 15,000 alpha to the power of negative 1/2. And then don't forget, chain rule comes into play here. So I need to multiply by a factor of negative 15,000. That's the coefficient of my alpha here. So that's another chain rule coming into play. At this point, I don't think there's any value in simplifying this expression. I just take a calculator and plug in 0. When I plug in 0, I get 0.3 times 30,000 to the negative 1/2 times 11,000. What's going to end up being minus 0.2 of 30,000 to the negative 1/2 times 15,000. I just moved the negative from the 15,000 out to in front to replace that plus. So I get 0.3 times 11,000 times 30,000 to the negative 1/2. What does that come out to be? 19.05. That's just this term, by the way. And then 0.2 times 15,000 times 30,000 to the negative 1/2, I get 17.32. But these are being subtracted, so I get roughly 1.73. Is that right? 1905 minus 1732, 1.73. And this is indeed positive. Remember, our goal was to show that this derivative would be positive at alpha equals 0. And we did. Okay, we are done with that question. We're going to now move on into 7.7. Actually, 7.7 I've already recorded, so I'm just going to skip this question entirely. It's recorded elsewhere, so I will give you the link to that recording, and then we can now move on quickly into the fourth problem. States W1, or I guess those are omegas. Omega 1 and omega 2 are equally likely. And then an expected utility maximizing decision maker has utility function of 2 times the square root of W over 1,000. Okay. The decision maker's $10,000 portfolio is allocated to 3 funds having random rates of return R1, R2, and R3, where Ri depends on omega as follows. Let's make this table. So omega 1 and omega 2 just represent states of the economy. This can mean they can be good or they can be bad. They usually have, that's usually what is taken in these sort of like investment portfolio situations, that we have one outcome where the economy is good and we have another outcome where the economy is bad. So there's one financial instrument, there's a second, there's a third, 1.08, 1.12, 1.06, 1.26, and the flip, 1.26, 1.06. This means, okay, we get the parallel interpretations hold for Georgia. Show that expected value of R1. Okay, this seems easy enough. So let's talk about R1. R1's only outcomes are 1.08 and 1.12. And they told us at the very beginning of this problem that the two possibilities, these two possible outcomes of good or bad, and I shouldn't necessarily ascribe good to the first column or bad to the second column, but these two states of the economy had a 50-50 chance. So we'll just, you know what, for the sake of whatever, let's just call them good or bad. So this was 50-50, there's 50% chance here, 50% chance here. So the expected value of R1 is very easy to calculate. You just take 50% of the first guy and 50% of the second guy, and you get 1.10. Cool, that was super easy. Also show expected value of R2 and R3. Cool, let's do those real quick. 1.06, 1.26. Probability here is 0.5, 0.5. And if I go to calculate expected value of R2, it is again 50% of the first value and 50% of the second value, which comes out to be 1.16. Yeah. Expected value of R3 is almost pointless in calculating expected value of R3 because all that happens over here. So R3, here's R3 changes. Just delete this. Like this blue. R3, R3. All that happens is that this guy swaps with this guy, or at least the order in which they're presented in the table. But guess what? That doesn't change anything about how this gets calculated. You do half of 1.06 and half of 1.26, add them together, and still guess what? You still get 1.16. So part A is now done. Let's get rid of all this. Part B, show that the standard deviation is equal to this. Standard deviation R2 is equal to the standard deviation. Okay, so there's one. Now we want to find the standard deviation. So probably shouldn't have deleted these. So let's go and find these standard deviations. Just gonna clean things up a bit to make my tables a bit easier to work with. Okay, let's start with expected value. Remember, the way in which we create an expected value table, or not expected value, but standard deviation, is by doing R3 minus this expected value squared. So this 1.126 becomes not 1.126, but 1.26 minus 1.16 squared plus, not plus, this is 1.06 minus 1.16 squared. Probability. And now let's go ahead and find this value, 1.26 minus 1.16. 0.101 times 0.5 times 2. I get 0.01. So variance of R3 equals 0.5 times, this guy ends up being 0.01. So does this guy. So I get 0.5 times 0.01 plus 0.5 times 0.01, which comes out to be 0.01. Okay. Now I hesitate to even bother doing it for the R2 because R2 was the same thing, but with this value swapped with this value. So guess what? The calculation is going to be the same. So it's going to be the same for variance of R2 as well. I'm not even going to bother wasting my time drawing the table for it because again, the table is the exact same. Let's do the variance of R1, however. So remember, if I want to do the variance for R1, I do R1 minus its own mean, square it, and that would be 1.08 minus 1.10 squared would be 0.0004. And this would be also 1.12 minus 1.10 squared, 0.0004, each with a 50% chance. We'll just say P. And this means variance of R1 ends up coming out being 0.0004. I guess technically they didn't want the variance. What do they want for part B? I think they wanted the standard deviation. Sure. If you want the standard deviation, you know how to get that. Standard deviation is the square root of 0.01, which equals 0.1. And so this is sigma. In a similar fashion, I would take the square root of 0.004 and get 0.02. So sigma here is 0.02. We'll call this sigma 1. We'll call this sigma 2 because sigma 2 was the standard deviation of the second and third financial instrument, these guys. And sure enough, we can see sigma 2. Well, sigma 2 equals 1.1. Sigma 1, as we just discovered, is 0.02. Indeed, it is the case that sigma 2 is bigger than sigma 1. So we are done on part B. Give the correlation of R1, or sorry, of R1 and R2 and the correlation of R1 and R3. That's the best way to do this. Yeah, let's just make a bigger table. So here's how we're going to do a correlation. We'll put R1 across the top here. We'll put R2 along the side. And we'll put the possible values of R1. R1 is 1.08 or it's 1.12. Whereas these guys are, wait a second. Let me pause for a second while I work this out. Oh, it was a quick fix. I thought that each of these values was going to be 0.25 in the interior of the table. I thought it was going to be 0.25 and 0.25, 0.25, and 0.25. This is not correct. In order to set up this joint probability table, just ask yourself, in the case of W1, which happens with the 50% probability, R1 and R2 are both low, 1.08 and 1.06. That's a 0.5 that goes here. In a similar fashion, in the second scenario, in the bad economy scenario, again, I don't know why this would be bad economy because the values are higher, but whatever. We get 1.12 for R1 and we get 1.26 for R2. That's a 0.5 that goes here. Now we're going to put zeros here and here. You might be wondering, well, why do we put a 0 here and a 0 here? Is there a scenario where R1 is equal to 1.08 while R2 is equal to 1.26? The answer is no. The economy is either in a good state in which case R1 and R2 are these small 1.08, 1.06 values, or the economy is in a bad state, in which case R1 and R2 is this 1.12 and the 1.26 values. It's not possible for R1 to be this value while simultaneously having R2 be this value, because it means you're in two possible states at once. You can't be in both the good economy and the bad economy state at the same time. You pick a state. So you're in the good state, you've got 1.08 for R1 and 1.06 for R2, or you're in the bad state, which you got 1.12 for R1 and 1.26 for R2. There's no mix and match with this. So that's why these guys have a probability of 0, because there's no scenario in which R1 is equal to 1.12 while R2 is equal to 1.06. And similarly, there's no scenario where R1 is 1.08 and R2 is 1.26. So these have to be ascribed a value of 0. How do you calculate a correlation? We're going to do this based off of the fact that, first off, you need the standard deviations from what we had before. So standard deviation 1 was 0.02. Standard deviation 2 was 0.1. You need a covariance, which we will find momentarily, of R1 and R2. And then the formula for correlation, this is it's a lowercase rho, so it looks like this. Correlation. It's a lowercase rho, RHO, equals covariance of R1, comma R2, divided by the product of the standard deviations, sigma 1 and sigma 2. I'll point out that you learned this formula back in Eco 329, whether you believe it or not, but you did. And I know for a fact that you did, or you at least got by without having to remember it at least. We have these values down here, sigma 1 and sigma 2. So I'm going to put 0.02 and 0.01, or not 0.01, just 0.1 down on my denominator. However, I need to calculate the covariance. So here's how covariance is calculated. That's going to be a little bit of a pain. Ready? You're going to subtract the mean of R1 from each of its values. So remember, the mean of this guy was 1 point. Let's remind ourselves. Expected value of R1 was not 0.1, but 1.1. The expected value of R2 was 1.16. So you're going to subtract the mean from the mean of R1 from each of the R1 values. You're going to subtract the mean of R2 from each of the R2 values. So I'm going to subtract 1.10 here and subtract 1.10 here. That's going to make these new values 0.02 and negative 0.02. And I'm also going to subtract the mean of R2 from each of its x values. So I'm going to subtract 1.16 from each of these. However, that's going to cause this to become negative 0.1 and positive 0.1. So I'm actually going to delete these values now. So now here are the new values on the interior of this chart. Okay. You're going to take each probability value on the interior of this chart. So this one, this one, this one, and this one. All of these probability values, and multiply them simultaneously by their R1 and R2 values. So you'll note that this guy here, 0.5, gets multiplied by a negative 0.1 to its left and a negative 0.02 to its right, as well as we're going to add this value, 0.5 times the positive 0.1 to its left and a positive 0.02 to its right. You could, if you wanted to, say plus 0 times the, let's highlight this 0. I would say times the positive 0.1 here, but the negative 0.02 here. But it seems kind of silly to do that because multiplying by 0 just gives you 0. So these terms don't even exist. What do I end up with after doing this multiplication? I get 0.1 times 0.02 times 0.5, and let's just double, so it ends up being 0.002. 0.002. So this is my covariance. And so this is going to sit up in my numerator. Don't need this guy, just this guy. Well, what's super convenient about this is my covariance ends up being positive 1. And this makes sense. Why are they positive? Why is it a perfect +1 correlation? Because when R1 is low, R2 is low. When R1 is high, R2 is high. And so the correlation here being that, how X and Y associate with each other is positive, because when one of them is low, the other one's low. When one of them is high, the other one's high. So that gives you a perfect +1 correlation. Now that script is going to flip when we go on to finding the correlation between R1 and R3. Here's all that changes when you do the correlation of R1 and R3. Now it's the case that the 0.5 and the, actually here, I'll just do this. These are now flipped. I don't have the old values from the table. I don't have the old, 1.08 or 1.06. But when this was a 1.08, R2 was more likely to be 1.26. So this was 1.08 prior. This is 1.26 now. This is the case where R1 is low and this is R3 now. R3 is 1.26. And so all that really ends up happening here, and you can see it for yourself. You can see that in the table. All that happens is they flip-flop from R2 to R3. So that kind of turned the graph on its head, kind of rotated the graph a little bit. So that said, my correlation is now, or my covariance, when I go to calculate this, we end up with a negative 0.1 times a positive 0.2, and we have a negative 0.02 times our positive 0.1, which gives us a covariance of negative 0.002, which when put in place of our correlation formula, this is now R3, this is now R3, and the nice thing about R3 or sigma 3 was that its standard deviation was still 0.1. That hasn't changed. But now my correlation is negative 1. And this again makes sense. When R1 is low, that is to say, when R1 takes on its lowest value of 1.08, R3 takes on its highest value of 1.26. So when R1 goes low, R3 goes high. When R1 goes high, R3 goes low. That's it. That's all we have really had to do for part C. Suppose half of the decision maker's $10,000 portfolio is allocated in R1 and the other half in R2. Give the decision makers expected wealth and expected utility. Okay. Did they give? They did. I was going to say, I forgot. At this point, I forgot there was a utility function associated with this. Let's get rid of some of this stuff. So our wealth is equal to, we're doing half of, we'll say 5,000 times R1 plus 5,000 times R2. Remember, we split our cash evenly between the two investments, R1 and R2. Okay, so we have $10,000. We're going to take $5,000 and put it in R1, take $5,000 and put it in R2. At this point, you're just going to calculate an expected value the way you did in Eco 329. So we'll take the expected value of both sides. This might end up seeming like a small blast from the past, because again, it is Eco 329. We're going to split the expected value. So this ends up being expected value of 5,000 times R1 plus expected value 5,000 times R2, which this is something you're allowed to do when the two terms inside an expected value are being added. Another thing you're going to do is you can take out any coefficient of a random variable in front of the expected values. This is 5,000 times expected value of R1 plus 5,000 times expected value of R2. Expected value of R1, we found way long time ago. This is 5,000 times 1.1 plus 5,000 times 1.16, which gives us 11300. That's the expected value of our wealth if we invest. And they also, I believe, want the expected utility. That's going to be a little trickier. Expected utility. So let's talk about our possible wealth outcomes, or utility out. Yeah, let's start with our possible wealth outcomes. So let's bump this up. Our wealth outcomes, if we put half of our money in R1, we are going to get, so let's say this, $5,000 into R1 and $5,000 into R2. If omega 1 happens, then we get 5,000 times 1.08 plus 5,000 times 1.06, which is, I think it's 10,700. However, if W2 happens, then we get 5,000 times 1.12 plus 5,000 times 1.26, which comes out to be, I'm going to say, what would that be? Is that an 8? Is that a 9? I'm going to say 11,900. Let's see if I'm right. Yeah, 11,900. And then this is 0.5 and this is 0.5. Don't forget, these are wealth values. These are not utility values. So I need to convert this to a utility table. How do I do that? I just take the wealth values that I've been given, circle these in red, plug them into my utility function above. So 2 times the square root of 10700 divided by 1,000 gives me 6.542. And taking the 11,900 and plugging in gives me 1.1900. Oops, no. 11.900. 6.899. Now let's calculate our expected utility. Let's be 0.5 times 6.542 plus 0.5 times 6.899, which comes out to be, give me a sec, 6.72, 6.72, 6.721. Okay, so investment strategy 1 gave us a wealth of 11, an average wealth $1,130 and an expected utility of 6.721. Okay, we're going to nuke a lot of this. This can all go away. Gone, 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 gone. Let's keep that actually. No, we don't need that. Okay. Redo it again. Suppose the another part E says, what if we did R1 and R3, give the decision makers expected wealth and expected utility? I think, honestly, oh, it's not quite the same thing. So it's going to be a little different. I'm going to change a few things here. This is now an R2 or an R3. I think the nice thing is, though, that this calculation is exactly the same. This calculation ends up being exactly the same. I should say the expected wealth. The expected wealth calculation ends up being exactly the same as the original expected wealth calculation. 5,000 for between both R1 and R3, split it up, the 5,000 come out. The expected value of R3 was still 1.16. So I again get 11,300. So let's copy and paste. Now, again, this is merely the expected wealth. We do not know the expected utility yet because it might be a little bit different. So let's get rid of this stuff here. We now need to make a wealth table. So let's get rid of this. Let's get rid of these. Let's get rid of these. Okay. What is our expected? What are our wealth outcomes? So if W1 happens, so now I want you to focus on only really only focusing on I'll do this. Row 1 and row 3. If W1 happens, we get $5,000 times 1.08. That doesn't change. Plus $5,000 times 1.26. Okay. On the other hand, if W2 happens, if the second column happens, we get $5,000 times 1.12, and we get $5,000 times 1.06. So 5,000 times 1.08 plus 5,000 times 1.26 gives me 11700. And if I do 5,000 times 1.12 plus 5,000 times 1.06, I get 10900. Of course, these are not utility values. How do I make them utility values? Take them, plug them into my wealth function. Okay, so my utility function for wealth. 2 times square root of 11.7 gives me 6.841. And then square root, 2 times square root of 10.9, 6.603. So this ends up being 0.5 times 6.481, 841 rather, plus 0.5 times 6.603, 6.722. Okay, so investment strategy 2 gave us the same expected wealth, of 11,300, but an expected utility of 6.722, just barely more than the expected utility of investment strategy 1. Whew, okay. F. You should have found that a decision maker's expected utility was higher when their portfolio was split between R1 and R3 than when it was split between R1 and R2, even though the expected wealth was equal. Explain what it is about correlation and diversification makes this true. Thankfully, we don't have to do too much math here. You've probably heard the phrase, don't put all your eggs in one basket. That phrase comes from the idea of, if we get kind of greedy here and we say, you know what, I'm going to go with this investment strategy where I pick R1 and R2, I'll get a huge payoff. Let's do this in green. I'll get a big payoff if the outcome is W2, because I get both 1.12 and 1.26, which are both better than the omega 1 outcome on the left. But we don't want to do that, or at least, again, we find that, and hopefully what you've seen over the past hour or so is that some insurance is better for people who are risk averse, right? By the way, this is a risk averse person. Hopefully that was obvious to you guys. Why is this person risk averse? Because we see their utility function is some sort of square root of wealth. Granted, there's a divide by 1,000 and a multiplication of 2 out in front, but that doesn't mean anything. It doesn't change the fact that the shape of this graph is concave down. So why would they prefer R1 and R3? Because in that situation, they're insuring against the bad outcome, right? No matter what, like they're saying that they're hedging, so to speak. If they choose R1 and R3, these outcomes, or these not outcomes, but these two financial instruments, if W1 happens, great, then I win here. I win in R3. If W1 doesn't happen, W2 doesn't happen, okay, well, we lost here, but we ended up winning over here. So that's the idea of diversification. No matter what happens, whether the outcome is good or the outcome is bad, I end up winning in one of these two columns, whether it be with R1 over here on the right or winning with R3 over here at the bottom left. So that's really all you need to say for part F. And then part G says, suppose now that the decision maker can choose how much of their portfolio to put on R1, R2, and R3 with the shares alpha 1, alpha 2, and alpha 3 being non-negative, give their optimal allocation. This is probably some sort of constrained optimization. Whew. All right, let's see if we can do this. I think we got it. I think we can do it. This is a nightmare, but I think we can do it. We want to maximize. It's some portion of their wealth. Yeah, sure. So maximize. Oh boy, 0.5 times the square root of, or so 0.5 times 2 times the square root of 10,000 times alpha 1 times 1.08 plus 10,000 times alpha 2 times 1.06 plus 10,000 times alpha 3 times 1.26 all over 1,000 plus, so this guy, by the way, this is all what happens if if omega 1 happens, plus, then there's the other half of the cases, which is 0.5 times 2 times square root of, which I can copy and paste, 10,000 times alpha 1 times 1.12 plus 10,000 times alpha 2 times 1.26 plus 10,000 times alpha 3 times 1.06. This is all divided by 1,000. This scenario represents omega 2. Notice that this is my wealth from R1. This guy is my, this entire term. It's my wealth from R1. This is my entire wealth from R2. And this term here is my, I hope it was obvious by now, wealth from R3. I'm going to pause this for a second because what I'm about to do is I'm not about to take a derivative and solve this constrained maximization problem. I'm going to try and type in a Wolfram alpha and see if I can answer. So pause real quick. I'll be back in just a second. Okay, I typed everything in. Time to share my screen on Wolfram alpha. One thing I did is I said maximize the square root of 10,000 times x times 1.08 plus 10,000 times y times 1.06 plus 10,000 times z times 1.26, each of the x, y, and z representing alpha 1, alpha 2, and alpha 3. And then I said plus the same thing over here on the right, subject to the following conditions. He told you that each one of x, y, and z are non-negative. I guess I should have said x is greater than or equal to 0, y is greater than or equal to 0, z is greater than 0, but it's fine. Because what ends up happening is it tells us that you should take half your money, put it in R2, take the other half of your money, put it in R3, and don't put any of your money inside of R1, which I guess makes sense. And that's your answer to the last question. You say alpha 1 is 0, alpha 2 is 0.5, and alpha 3 is 0.5. Okay, I'm going to take a break now. This wraps everything up with regards to the expected value diversification section, so to speak. And then next section should be possibly game theory. See you guys in the next part.